This has us find the eigenvalues and eigenvectors of a given 3x3 matrix. See our matrix A in front of us here. Our first step here is always to find the eigenvalues, which means we want to start with A minus lambda I and then find the determinant. So A minus lambda I is given by subtracting lambda off the diagonal entries of this matrix. Then we can go to find the determinant. So in this case, we look for the easiest row to work this out on. In this case, it's row 1, because it has only one non-zero entry in it. So working this out, the determinant of A minus lambda I is going to be given by -1 to the 1 plus 1, 1 minus lambda. The determinant of the opposite minor, 1 minus lambda minus 2, 2 minus 3 minus lambda. And then we work out that 2 by 2 directly. It is a AD minus BZ 2 by 2 matrix. And so I will end up with here a 1 minus lambda times 1 minus lambda minus 3 minus lambda plus 4. 1 minus lambda times lambda squared. I have plus 3 lambda minus 1 is plus 2 lambda, minus 3 plus 4 is plus 1. I'm noticing my mistake. I dropped the minus sign from the top here, so this is -1, -1, -1, -1. And this here is lambda plus 1 squared. Negative lambda minus 1, -1 minus lambda times lambda plus 1 squared, which is actually negative lambda plus 1 cubed. So here we have a triple repeated eigenvalue at -1. Now, because it's triple repeated, we could expect to see anything 1, 2, or 3 different eigenvectors, and by different I mean linearly independent eigenvectors for this value. It could be any of those. All we can do is try to work it out and see what we get. So if I take lambda equals -1, I need to add 1 on the diagonals here. So I will see 0, 0, 0, -3, 2, -2, -3, 2, -2, which I can then rearrange and row reduce because the bottom two rows are the same to give me exactly this. -3, 2, -2, 0, 0, 0, 0, 0, 0. Now if we look at this, we see we only have one not all zeros row, so there's only one pivot element, which means here both v2 and v3 are free variables. This means that I'm going to get two different linearly independent eigenvectors here by picking linearly independent options for the v2 and the v3 of this. So the key point here is v2 and v3 are both free variables. How do we make this work? We get our two vectors by, so our two vectors will come from v2 is 1 and v3 is 0, and v2 is 0, v3 is 1. It's kind of like your standard basis for R2, 1, 0, and 0, 1. We're going to use that to give us two definite linearly independent eigenvectors that'll both solve this problem. So our key equation here is that -3v1 plus 2v2 minus 2v3 must be 0. So in case 1 over here, where v2 is 1 and v3 is 0, this says that -3v1 plus 2 equals 0, 3v1 equals 2, v1 equals 2/3, giving rise to an eigenvector here of 2/3, 1, 0. On the other hand, if we pick v2 being 0 and v3 being 1, we will end up with -3v1 minus 2 equals 0. -3v1 equals 2, v1 is -2/3, and an eigenvector then of -2/3, 0, and 1. Now those two vectors are linearly independent. One is not null to the other because there's the 0 and the 1s that line up in the way that they do, and they both solve this equation right here, which is the only thing that define being an eigenvector of eigenvalue -1. And so those are two linearly independent eigenvectors for this matrix in this problem. We know there's not a third because there is an equation they satisfy. Right, I only had two free variables, so I only expect to get two independent eigenvectors. if I got 3, because the whole matrix is all zeros and there's no constraints, so the 3 can be anything, and I get the whole space. But in this case, I get the 2 different eigenvectors here for lambda equals -1. These are 2 linearly independent eigenvectors for lambda equals -1. This is still a defective eigenvalue. The power was 3 in the polynomial, and I got 2 independent eigenvectors. It's still not quite enough. It's better than if I only had 1, but it's not quite all the way to 3 that we would need to make all this work out in the appropriate way. But that shows an example of having a repeated eigenvalue, in this case a triple repeated eigenvalue, that has 2 different linearly independent eigenvectors.